This video is for the accepted paper, Neural Implicit Manifold Learning for Topology-Aware Density Estimation. This work is by me, Brendan Lee Ross, and my colleagues, Gabriel Loaiza-Ganem, Anthony L. Catarini, and Jesse C. Cresswell. It was accepted to TMLR in December of 2023. In generative modeling, we often encounter diverse and complex data, and in particular, it tends to have manifold structure. For example, if our data is high-dimensional, we can say it satisfies the manifold hypothesis for the most part. Also, in nature, datasets often lie in manifolds just due to the smooth constraints of physics. So we're able to model this data well, but our generative models often exhibit pathological behavior, such as exploding inverses and assigning higher densities to OOD data points. These pathologies suggest that we don't fully understand the interplay between our generative models and the geometric structure of the data, and there is past work to back up these ideas. As a result, these pathologies highlight a core need in generative modeling, which is to design generative models whose inductive biases fit the true mathematical properties of our data. With this motivation in mind, let's establish our problem setting. Assume our data distribution sits on a lower dimensional submanifold M of some ambient n-dimensional Euclidean space. This is a common and principled way to model data in the presence of the manifold hypothesis. We're going to further assume that our distribution has some density p star x defined on M. For example, in this image, the ground truth density is shown on the left. It's a von Mises distribution on a circle in R squared. From this distribution, we have a data sample, which is depicted on the right. Our goal is going to be to perform density estimation on this data, or in other words, to infer the density on the left from only the data on the right. In a 2022 paper, Loaiza-Ganem et al. Outline a procedure for density estimation with push-forward models. The first step, you pair the decoder f theta with an encoder g phi, which maps from the data space back to the lower dimensional latent space. You then train g phi and f theta to invert each other on the data. One way to do this is by minimizing a reconstruction loss, which we can write as an expectation over the ground truth data distribution. Often, extra regularization terms are added as well. There are also other ways to train g phi and f theta to invert each other, such as by minimizing a bidirectional adversarial loss. Once this is done, you learn a density p psi on the latent encodings of the data. At optimality then, densities on the manifold are available using the following expression. The density at x on the manifold is going to be equal to the density of that point encoded in latent space modulated by a Jacobian determinant term. This Jacobian determinant term looks similar to the one used in normalizing flows, but is actually a generalization to situations where the map goes from low dimensions into higher dimensions. The reason this works is that when you perform this procedure, f theta at optimality becomes a bijection between the data manifold and the latent distribution. However, for general manifolds, this is impossible. As we show in the image here, it is not possible to map a one-dimensional Euclidean space, for example, directly onto a circle in a smoothly invertible way, which is what push-forward models in this procedure are trying to do. Note that you will always have some kind of artifact, such as the one here, where you are unable to learn the manifold. In 2020, Cornish et al. Showed that when the manifold is topologically mismatched, such as in the situation prior, the bi-Lipschitz constant of f theta will diverge to infinity as you fit f theta to the data, which renders it numerically unstable and making density estimates unreliable. As a result, we have to pick a place on a continuum between expressivity and stability, and in this push-forward modeling situation, you can't have both. In this work, then, we propose another way to express manifolds. Push-forward models have their manifolds defined by a bijection between the support of some latent distribution and the data manifold. Another way to express manifolds, which is common in geometry but is not used in generative modeling, is to define them as a zero set. This means the set of all points that map to zero, for some map that maps from the data space into some other space. In this context, we want the map to map from the data space Rn into Rn minus m. This can be thought of as applying n minus m constraints to the data, leaving m degrees of freedom and hence creating an m-dimensional manifold. A simple example of this is the circle in R squared, which is the zero set of f, where f of xy equals to x squared plus y squared minus 1. In this context, we call f a manifold defining function, or an MDF, and m is equal to the zero set. It's said to be implicitly defined. Note that here already, with this example, f is able to model a more complex topology than was possible with push-forward models, as we showed in the previous slide. Now let's see our method. Our goal is to train a neural network f theta to be an MDF for our data manifold M. Here's an example of what one might look like for the circle example we showed previously. See how it intersects 0 exactly on the data manifold. What we call the full rank 0 set theorem gives 3 conditions for f theta to be an MDF for a data manifold. One is that it's 0 everywhere on the manifold, 2 is that it's non-zero off the manifold, and 3 is that it has full rank everywhere on the manifold. This third condition ensures that the manifold has the correct dimensionality. Thinking about f as a set of constraints, you can think of this condition as enforcing that none of the constraints are redundant at any point on the manifold. Combining these 3 conditions together results in the following manifold learning loss. The loss has 3 terms, each corresponding to one of the conditions from the previous slide. Minimizing the first term causes the MDF to be 0 on the data points. Maximizing the second term causes the MDF to be non-zero on data points that are not on the manifold. The third term causes the Jacobian of the MDF to have a minimum singular value higher than some hyperparameter eta. For more details on how we derive these terms and how they're computed, please see the full paper. At optimality, we arrive at m theta star, which is the zero set of our MDF f theta star. This should match the true manifold M. So once this procedure is complete, we have an MDF f theta star, which determines some manifold m theta star. But this is just a manifold, not a generative model. We now need to learn a density on top of that manifold. To do so, we use energy-based modeling. Energy-based modeling is when you parameterize your distribution with an energy. This is a network, in this case, E psi, which corresponds to the negative log unnormalized density of your data. Note, however, that to recover the implied density from your network, you need to normalize over the entire data space. That's this integral here. This, however, doesn't make sense for our context because we're only modeling a density on top of the manifold, and thus we need to integrate only over the manifold. We also need to use a different measure, the Riemannian measure of the manifold here. We call this new model a constrained energy-based model, and we denote its distribution by p theta star psi. EBMs are typically trained with an algorithm called contrastive divergence. Contrastive divergence allows you to compute the gradient of the log likelihood without having to compute the log likelihood itself. This allows you to optimize the log likelihood without having to compute the intractable integral that we saw on the previous slide. Note, however, that computing this gradient requires you to sample from your model. In our context, then, we have a constrained EBM, and we have to be able to sample from that in order to train. To sample from a constrained EBM, we use constrained Hamiltonian Monte Carlo. This is an approach designed for implicitly defined manifolds. We focus on constrained Langevin Monte Carlo, which is a simple special case of constrained Hamiltonian Monte Carlo. To our knowledge, this has not been used before in the literature when F is a neural network. So to do this, it requires some tricks using automatic differentiation and numerical linear algebra to actually scale this up to larger data sets. This results in our new algorithm, efficient constrained Langevin Monte Carlo, which we encourage you to check out in Algorithm 1 and Section 3.2 of the paper. In summary, our method consists of 2 steps. The first is to train a network f theta to satisfy the full rank 0 set theorem. The second is to learn the density within the resulting manifold m theta star by fitting a constrained EBM E psi. The likelihood of E psi can be maximized with contrastive divergence, which requires sampling, and samples can be computed with our proposed algorithm, efficient constrained Langevin Monte Carlo. The full model, with these two steps together, is called an energy-based implicit manifold, or EBIM. Next, let's see how the model performs in some experiments. We experiment on two categories of data. One is known manifolds with non-trivial topologies, and the second are image manifolds. For the first experiment, we model a mixture of two von Mises distributions on disjoint circles. The ground truth is depicted on the top left here, and we train a vanilla EBM on this as a baseline. The vanilla EBM is able to learn the topology pretty well, but it still learns a full dimensional density, which is not correct. We also compare to a push-forward EBM on the bottom left here, and although this is able to accurately learn a density on a manifold, it is not able to correctly capture the topology of the distribution. Our model, however, is able to perfectly learn the topology and then also learn the density within. We emphasize that the model is learning the topology entirely from data samples and has no a priori knowledge that the data is on a circle. We see a similar story for geospatial data. This dataset is the set of global flood events from the Dartmouth Flood Observatory. Since these events occur all over the Earth, they have a spherical topology, and push-forward EBMs, which are depicted in the middle, are unable to handle this. Since they cannot capture the topology properly, there appears to be some instability in the densities, and the densities are not accurate. On the other hand, ours captures the densities well. Our model also shows strong performance on a dataset of amino acids. So an interesting thing about some amino acids is that they can be characterized by a pair of dihedral angles and thus have a toroidal topology. The ground truth is shown on the left, and if we try to model this with a push-forward EBM, it fails drastically to learn the topology. On the other hand, our model captures the topology despite the fact that the data is fairly sparse along the torus, and also captures the density within. We also evaluate all of these examples numerically using the Wasserstein distance and find that our densities are better than push-forward EBM densities. In this next set of experiments, we model image manifolds, namely MNIST and fashion MNIST. The first two comparisons we make are to push-forward models which can do density estimation of comparable size to our model, and we find that ours outperforms it. We also compare to a normalized autoencoder of comparable size, because although it's not a density estimator, it has some similarities in training methodology. Our model is competitive in performance with the NAE. For this last experiment, we study an interesting property of MDFs, which is that they have some degree of composability. Consider two MDFs, F1 and F2, for manifolds M1 and M2 respectively. The union of those two manifolds is defined by the product of the two functions. The intersection of those two manifolds can be defined by the concatenation of the function outputs. Here's an example. We take a spherical distribution and learn it with an MDF. We then make two copies of this distribution by translating it slightly to the left and slightly to the right. In this middle image, we create a new MDF by multiplying the two MDFs, and that represents the union of the two manifolds. In the image of the right, we take the intersection of the two manifolds by concatenating the function outputs of the MDFs into a new one. What's useful about this is that it expands the number of different structures we can model, because we can model more than just manifolds now. We can model unions of different manifolds and intersections of manifolds. Here's an example on image data. We started by creating two overlapping image manifolds from different classes of MNIST. First is the 1 class unioned with the 4 class, and the second manifold is the 4 class unioned with the 7 class. So we have now two image manifolds, both of which are unions of two classes. We train an MDF on each of these unions and use manifold arithmetic to compute their intersection. This would look like this. As you would expect, the resulting samples mostly look like 4s. But you also had some examples that look like they're in the intersection of the 1 and 7 class, and some samples that even look like they're in the intersection of the 1, 4, and 7 class. Here are some takeaways from the work. One is that push-forward models are unable to model densities on topologically non-trivial data manifolds, despite the fact that they're the prevailing paradigm for modeling densities on manifolds. To remedy this, we propose the EBIM, which consists of two steps. One is to model the data manifold as the zero side of a neural network, and then we model the density within using an energy-based model with constrained Lagrange dynamics. We then show how these can be trained tractably and scaled to image data. Thank you for listening.